Hi everyone, I'm Chris and welcome back to the lecture on linear regression of this machine learning course. This section is about the cost function for regression. We have a model y tilde depending on the independent variables x. This can be a single variable x or multiple variables x1, x2 and so on. The model is used to estimate a target variable y. The model has trainable parameters denoted by beta 0 up to beta capital L. These parameters are subscripted at the function y tilde. Different values for the trainable model parameters beta lead to different functional relations of the model. How do we know what the best values for the trainable beta parameters of the model are? In other words, with respect to a given dataset, how can we measure the quality of the model to the data? So the model quality is calculated for a given dataset. Let's reconsider our real estate price estimation dataset. Here, highlighted in green, is a training data. The training data has different features such as length and width. These features are represented by our independent input variables x1, x2 and so on. They can be collected together into a single feature vector. So this vector x contains all input variables x1, x2 up to x capital K. Consider the feature values of the ith data point of our data table. This data sample has variables x1i, x2i and so on. So a second index I indicates the sample of our data. If we represent this in a vector, we put an additional index I to the vector to indicate the ith data sample. A cost function measures the quality of the model fit to data. Note that a cost function is often also called loss function. An example for such a cost function is the mean absolute error. Let's take a look on the right side. This cost function considers the differences between the model with certain parameter values and the corresponding true values of the target variable y. These differences are the distances between data and model along the y-axis. This is sketched here in blue. The mean absolute error takes these distances directly into account. Therefore, it takes the true target value of a data point yi, where I is the index of a data point. Then, it subtracts the model estimation for the corresponding independent variable values, vector xi. The absolute value then gives the distance. The mean absolute error cost function takes all data points for a given data set into account. So a summation over all data points by the index I is performed. The expression is normalized by the number of data points in the given data set, capital N. This is why the cost function is denoted as mean absolute error. So, it gives the mean distance of a data point to the model for a given data set. Probably the most popular cost function is mean squared error. The formula is here highlighted in blue. The key difference to mean absolute error is that the mean squared error takes the squared distances between model and data into account, instead of just the absolute values. So here we have 1 over capital N, the number of data points in the dataset, times the sum over all data points by I of the squared difference of the true target value yi minus the model's estimation for the vector xi. The vector xi contains the values of the independent variables which correspond to the target true value yi. On the right side, the contributions to the summation in the mean squared error are displayed. The squared distances between model curve and data points are represented by blue squares. In contrast to the pure distances in the mean absolute error, the squares penalize single large deviations much more. For example, a contribution of 1 in the sum of mean absolute error is still a 1 in the mean squared error, but a contribution of 10 in the mean absolute error is now 100 in mean squared error. So we have for mean squared error larger contributions of data points far from the model in comparison to mean absolute error. Single data points that differ significantly from the other data points are called outliers. So mean squared error is much more sensitive to these outliers in the data than mean absolute error. Let's reconsider the linear model with a single independent variable x. The model was beta 0 plus beta 1 times x, with the trainable parameters beta 0 and beta 1. The mean squared error takes the squared distances between data and model into account. Thereby, the target's data value yi is used, and it is compared to the corresponding model value at the data point's location xi. So the corresponding model contribution to yi is beta 0 plus beta 1 times xi. Now we substitute this model into the mean squared error cost function. Then we obtain the expression highlighted in blue. On the right side, two different linear models are sketched. The model with optimized parameters is closer to the data. Thus, the squared distances between model and data are smaller compared to the other model with more random parameters. So the latter one leads to a larger cost function value. Next, let's apply the multiple linear regression model to the mean squared error cost function. This model takes capital K independent variables x1, x2, up to x capital K. We set x0 is equal to 1 to obtain a concise representation of the model y tilde. This is the sum over k of beta k times xk. The summation starts at k is equal to 0 to include the y-intercept because we defined x0 is equal to 1. We can use data points to calculate the mean squared error of this model for specific values of the model parameters beta. The ith data point is yi for the target value and x1i, x2i, up to x capital Ki for the independent variables. Note that we have two indices at the independent variables data points. The first corresponds to the dimension because we take capital K input variables into account. The second denotes the specific data point in the dataset. The resulting mean squared error for the multiple linear regression model is then shown on the upper right. Similar to the two indices at the data points variables, we have two summations. The first one is the mean squared error related summation over all data points. The second one is over all dimensions starting from k is equal to 0 to include the y-intercept to capital K. Besides mean squared error and mean absolute error, there are plenty of other common used cost functions for evaluating regression models. For example, the weighted mean absolute error. This cost function is identical to the mean absolute error, but has an additional factor wi for each data point. Each data point yi xi is weighted by wi to scale the error contribution in the cost function. So the weighted mean absolute error can take different scales in the target variable value yi into account. The scaling factor wi can be the inverse of the target value yi. In this case, we have the so-called mean absolute percentage error. This cost function is pretty interesting because it considers percentage deviations of model and target variable. For example, consider a price estimation. Let's say that the difference between model and data is $1. If the true value is $100, this means our model has a 1% error to the data. And exactly that is the error contribution to the cost function. If the true value is $10, the deviation is 10%, and so on. So this cost function can be very useful if a broad value range is considered and percentage deviations are natural to measure the model quality. Section finished. If you like this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.